Hello and welcome to helpyourmath.com. In this video, we're going to look at graphing cubic functions using the parent function and our knowledge of transformations of functions. First, let's review the parent function of cubic functions. The equation for the parent function would be f of x is equal to x cubed. So this is our cubic function, and then some key points on it. So there's always that one key point that all of these parent functions have. And on our cubic function, it's the origin, it's 0, 0. So I'm going to put 0, 0 in the middle of my table. 0, 0. And then we're going to use our famous -2, -1, 0, 1, and 2. And if you don't know these values, just plug them into the function. If you do, that's great. So -2 cubed is -8. -1 cubed is -1. 1 cubed is 1, and 2 cubed is 8. So the graph of the parent function would be -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And so it has like a curve in it. Let's see if I can do it. And so a few things about our cubic function. I'm actually going to do this so that you can see the perfect graph instead of my terrible graph. Let me get rid of my terrible graph. Okay, so you can see the key points. Notice that from -infinity to 0, this is concave down, and then it hits 0, and then it turns concave up. Concave down means that it's facing down, the curve is facing down, so see it's like facing down here, and then it switches and it's facing up here. So that's what a cubic function does. That point, I call it the point of inflection. We can call it whatever we want. That's the point that we want to find when we're trying to graph these cubic functions. And so the way we're going to find it is just like with any other function. There's going to be changes within the function itself. So when we see something inside, that's going to move the graph left or right. If h is positive, it moves it to the right, and if it's negative, it moves it to the left, but beware of that minus sign. And then if there's changes going up or down, vertical changes, we would see that it would be outside of the function and it would be added on away from where the cube is. So those are the two types. There's also, we might see the negative here. If we see the negative, that's going to turn this graph upside down. So where we see it's going down towards -infinity as the numbers get smaller and smaller. If there's a negative, it's going to be up here. And if it's a negative, it's going to be down here instead of going that way. And we could also have stretches and shrinks if there's some value in front of the thing that's being cubed. Okay, let's look at some examples. Here we want to sketch a graph of g of x equals 2 plus x cubed. Notice that this is kind of written a little strange. It might be more comfortable for us, or what we're used to, is if it said x cubed plus 2, right? We want to make sure that we're using that plus 2 appropriately. What does that plus 2 mean? It means that we're taking all of those y values and we're moving them up by 2. So this is taking the graph and moving the graph up 2. I'm saying and writing what I'm saying. If you want to make a table of values, you can, if you remember those key points. So remember that one of the key points was -2, -8 on our parent function. We're going up 2, so that means we're adding 2 to our y values, which means that point would be at -2, -6, right? If we add 2 to -8, we get -6. So -2, -6 would be right here. And then -1, -1 would now map to, if we move it up 2, it would still be -1 as our x coordinate, but the y coordinate is now 1. So it's going up here. And that special point that we're looking for, right, our point of inflection, which I'll call our POI, the point of inflection is still going to have an x coordinate of 0, but the y coordinate moves up 2. So we have 0, 2, which is right there. Then we have 1, 1 on our parent function. We're going to add 2 to the y. That's going to bring us up to 1, 3. 1, 3. And 2, 8. That's going to bring us up to 2, 10 on this transformed function. Now, I'm kind of using this based on the parent function. You can absolutely just make a table of values. If you're going to make a table of values, you always want the middle value to be this point of inflection. So if nothing else, find that point of inflection and then work around the point of inflection. So this graph is going to look very similar to our parent function. It's just moved up 2. And again, I'm going to try my best, but we know my graphing skills are subpar. So that's what it should look like, and that's what it actually looks like. So you can see it's got the concave down before 0, 2, concave up after 0, 2. How about this example? So first, let's identify our point of inflection. Where's the point of inflection? It's going to be at, this is going to be 2, -3. So our point of inflection this time is going to be right here. And again, if you are concerned, really what you're looking for the point of inflection is you want this to become 0. So you could just set this equal to 0 to confirm that that really is the x-coordinate. And then once you know the x-coordinate, you can figure out y, because this thing will cancel and you'd be left with just that y term behind it. Okay, so we're working around that. Otherwise, there's no changes, right? So if you want to make a table of values, that's fine. If you want to use the parent function, that's fine. I find that using the table of values makes people feel a little more comfortable, but remember, we're going to plug in 5 values here. And what's the middle value going to be? The point of inflection. So we're going to use 2, -3. We want to choose points around 2. So 2 away from 2 is 0, 2 away from 2 is 4, then 1 and 3, right? So this should just look like a set of 5 numbers in a row, 5 consecutive numbers. We don't want to do anything weird here. We just want these 5 numbers. Plugging in 0, so if I plug in 0, that's going to be 0 minus 2 cubed minus 3. Well, this is 0 minus 2, -2. -2 cubed is -8, and -8 minus 3 is -11. Next, we're going to plug in 1. 1 minus 2 cubed would be -1. -1 cubed is -1, and -1 minus 3 is -4. This one we already have. Now we're going to plug in 3. 3 minus 2 is 1. 1 cubed is 1. 1 minus 3 is -2. Plugging in 4. 4 minus 2 is 2. 2 cubed is 8. 8 minus 3 is 5. So now we have some points here. Whoops, I don't think I'm going to have, well, I'll just put it right there. 1, -4. And this should look familiar, right? Right around that point of inflection, we should have this diagonal one and this diagonal one. So we should have 3, -2. Yes, we do. 3, -2. And then 4, 5 is up here. And we can make our nice concave down, switches to concave up. And it should look like that. I'm getting better at these, sort of. That's what our graph will look like for g of x equals x minus 2 quantity cubed minus 3. Let's look at one more example. Here we want to sketch a graph of g of x. Okay, so first, the point of inflection. Let's figure out what that is. That's going to be at 1, 4. There's also something else interesting about this equation. We have the negative here. So normally our parent function looks like this, but this negative means it's going to be the other way. It's going to look like this. So that's what we're expecting, but we can make our table of values because I know that generally makes us feel better. What are we going to put in the middle of our table of values? We are going to put that point of inflection 1, 4. So I'm going to build 5 spaces here. I'm putting 1, 4 right here. Now I'm just going to put 5 consecutive numbers where 1's in the middle. So we have -1, 0, 1, 2, and 3. And we can plug in, or if you kind of know what's going to happen, you can try to figure this out too. I will go ahead and just plug in. So we have negative of -1 minus 1 cubed plus 4. Inside here, this is -2. -2 cubed is -8, but then we negate the negative, so it becomes a +8. +8, right? Hopefully this makes sense. Let me just write this down. So this is -8, but we have this negative in front. So the negative of the negative becomes positive. 8 plus 4 is 12. So we start out -1, positive 12, which will be up here. Then if we plug in 0, so we have negative of 0 minus 1 cubed. 0 minus 1 is -1. -1 cubed is -1. And then the negative of -1 is +1. So we end up with 1 plus 4 is 5. So 0, 5. Then we should have that point of inflection better be right here because we don't have any vertical stretches or shrinks. 1, 4, 1, 4. Gorgeous. So we are expecting, can you tell me, what are we expecting the next point to be? It should be 2, 3. It should be right here. Let's verify that it really is 2, 3. 2 minus 1 is 1. 1 cubed is 1. Then we negate that. So we have -1 plus 4 is 3. Confirmed. And last but not least, plugging in 3, we have -3 minus 1 cubed plus 4. 3 minus 1 is 2. 2 cubed is 8. Negate the 8, we get -8 plus 4 is -4. So 3, -4. We were expecting this graph to have that reflection. So this does look pretty good. I'm going to try my best. I'm kind of off the screen here, so I have to freehand this a lot. Of course, all my other graphs are terrible, so this is no exception. And so our graph should look like that. And the computer confirms, hey, it looks about average. These have been examples of graphing cubic functions based on the parent function and transformations of functions. Thank you so much for stopping by.